Hello, my name is Mwang'onda. Today I will walk through. We are implementing LAM. So LAM will have two ports, the light port and the lead port, as you all know. So basically, before starting designing the LAM, we'll start now sketching on how the LAM look like, so that our implementation should be clear. So today we'll be designing like our sketch. We'll use draw io in Visual Studio Code. So basically here I'll just search like the rectangle, rectangle. Oh, sorry, rectangle. Okay, let me come on like the normal. So I will just take this kind of rectangle square kind of it. So this one will be like our lamp, how the lamp it. So basically here I just want to know our ports will be looking like. So this will be like our inputs. Okay, so oops. Okay, this will be our inputs. Okay, let's move a little bit. So we just be copying, um, copying here, pasting here. Okay, pasting here. So we'll have different kind of inputs. Basically our inputs will be, they will be almost 7 inputs and 1 output. So the output will be from the I will explain. So our input will be 7. So let me, these lines will be 7 lines. Okay. Okay, 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. Okay, so the other one will be here. Okay, 6. And okay, oh, 1, 2, 3, 4, 5, 6. Let it be 7 input. Okay, and 1 output, the data output. So basically we just have to write the text here. So the first input will be clock, but every module should have like the clock. So that's most of the time. The second one will be our reset. Reset. The third one will have like the enable, but the enable will have to enable. Write enable. I will just write the shortcut, and the read enable. These are the inputs. Read enable. So we just be like read enable to be like rain. Then we'll have the write address. Write address. And read address. Read address. Then our data which we want to input. So it will be data in. Yeah, it will be data in. And finally we'll have the data out. So you just maybe edit this in, be the data out. So this will be our dual-port LAM. Dual-port LAM. So dual-port LAM will have, you can see, first input will be like the light, the first port will be like the light enable. Will have like the light enable and the light address and data in. So for the another port, we have like the light read enable, read address, and the data out, because the reading, you are reading from the memory, and the writing, you are writing to memory. So basically, I think here um, to be very specific, let me shift this enable should come this way, so that we should be specific with these ones. It will be coming from this port. Let me take this read enable and the read address. Oops. So come this way. Yeah. And anyway, we will just be leaving here. So this one will be read address, so that it should make a little bit sense when I'm doing this one. This side is like the right one, writing into the memory. The other side, the other port, the other side is the okay. Oops. Okay, this side, any hardware, we have like the clock and the reset one. Reset, most of the time when you have maybe some errors and stuff, you click the reset button so that you should go back to the normal state. And this one, this port is like the writing into the memory. This one is reading from the memory. So what basically here we will be doing is, first of all, the RAM will receive the data, will be writing in. So once the write enable is asserted, um, the data in will be, the write address will receive the data in which we want to write into the memory. So it will store the data which you have come, it has come from the, like, which you want to write in. So that write address will just carry the data, which it will store the data which have already the data in have carried into the memory. Then if you want to read, you send the, you will set the read enable. So once the read enable is accepted, then um, we will put the address. Maybe for this example, the address, maybe if it was the data for data in has been written from the on the address 001. So here we just query the data from 001. So and the data out will give us the data which we wrote in the memory. So basically how the whole RAM will be implemented. This is the sketch on how we are going to implement. So this is a sketch on how we want to implement the RAM, dual port RAM. Yeah, thank you very much. And now we'll go straight away into implementation. We'll write the our RAM in Verilog and the test bench for it. Thank you very much. Hello again. I'll be using Vivado as a simulation part, and our implementation will be using Ubuntu. It is Ubuntu 20.04. So basically, I will just sign in. Okay, this was the which implemented before. Let me cancel it, close without saving. Let me clear. CD. Okay, let's jump in and start our project. I'll navigate into documents, and we'll create a folder which we want to be working on. So cd documents. So here, how many project folder we have? 3 folder, but I will create another new folder which we'll be working on. So we'll implement using the Verilog. We'll create the module and the test bench, and that later on we'll just work on it. So let's jump into it. Okay, I'm creating as the Linux in basics, so we'll just create the folder called lam. So and we'll enter inside that directory called lam. So we are in it. So if you look, we don't have anything. Minus we don't have anything. I think we just have hidden folders. I think We don't have anything we want, so we'll create from scratch. So basically, let's create our the first file called the lam.v. So we are using nano. For those who are familiar with Linux, I'm using nano. So we'll create first of all, we are jumping in using the Verilog. So if anyone who is familiar with the Verilog, you bear with me. We are starting with two kind of um, uh, two things. So first, we are using module. Okay, so module to be module lam. Let's call it module lam. So we'll be closing here, and here the bottom will just end the module because I just don't want to forget at the end of it. Yeah, so we are starting now. So inside there we'll declare now our parameters on the basically. Sorry, I just need to use this kind of thing because we write, yeah, we write our variable, declare our variable. So I say that as said first. So if you back then where we were creating those kind of stuff, we said that we will be using two things. We have 7 inputs and 1 output. First of all, we have like input clock, then will be comma, then you have input reset. So like I have divided before, then I will just come like these are the light interface. I can say light interface, which is on port 1, port 1, port 1. Let me, yeah, these are just a comment. I'm commenting so that you should be able to read the code properly. Okay, so we have in during the light interface, we have how many? I think inputs we have like 3 input. We have like 3 inputs. We have 3 inputs basically. Light input, right enable, just light in short, then close, input right address, input right, not lighting, we will be data in. But here there's one thing which we forgot. Let me put everything, and this we are going now for lead port, lead interface, which was the other side during the implementation when designing, which will be on port 2. Okay, so it will be input read enable, it will be input read address, and the last one will be output. So our output need to be reg, output reg data out, data out. So as you can see, we forgot one thing. What did we forgot it? We forgot the size of the address and the size of our data which we are dealing with it. So basically, we'll declare on global one. So first of all, when you are declaring on top of it, we'll just include the hashtag. So hashtag will include this and that one before the input down. So here we just want to write the globally. So here instead of write parameter, we'll just like address size, add size is equal to it will be easy. So for the address, I think based on if you follow another, I think we'll come up with another video which will be explaining how do we find the address size of the lamb and how do we find the data size. So if basically here I just put it to be Raven, then in parameter data size which we are dealing with, let's take to be 32-bit. So our data which we'll be dealing will be 32-bit. So here on the light address, inside here after input we'll put two quotes. Then inside here we have to write something like 32-bit we write in this format. So this is a address. So since address is 11 bits, so it will be like 10 to 0. So it will count from 0, as you know, I think from 0 to 10. So those are kind of index. So basically here I don't want each and every time to be writing 10 0 10 semicolon 0. So I don't want something. That's why I implemented on top of there like parameter add size, address size. So here I'll be just like writing something like add, which is address size, add size, then -1. So basically here, instead of writing 10, it will be 11 minus 1. So it will be 10 semicolon 0. So counting from 0 to 10, it will be 11 bits. So it's 11 bits for the address size. Likewise with the data size. So the data size will be also input something like that. So instead it will be just data size -1, then semicolon 0. Let me be consistent here. Changing the first one here, it will look like something like that. So it will be the same way with this one, the lead address. So we'll just input in this format. It will be address size -1 0. So instead of writing 10 semicolon 0, it will be like address size -1 something. So this one is very important when you're writing up with dealing with the maybe we are dealing with 100,000 lines of code. So instead of changing everywhere, we just change the number of bits here. So everywhere will be applied instead of using this kind of stuff. So here, that's what we'll be doing. So in the lead, will be out this ledge, and yeah. So here we'll write instead of like it will be data size -1 0. Yes, that one. Yeah, something like that. So now we are done writing or declaring all our inputs and our variables which we will be using in the coding. So down here we will now like the memory declaration. Outside this one we'll write the memory declaration. Memory declaration. So our memory declaration will be a range which will be storing range in a hardware modules. Will be the register. It stores have got some kind of stores by law. The other one which we call it we have ledge and the wire. So wire is just like transmitting the data from there. It doesn't store. So that's why we are writing a ledge, because it will be storing some kind of data in it. So we are declaring our memory here. It will be range. Here we'll put the size of our lamb, not size of our lamb, it will be size of the weight, like size of the weight which we are dealing with it. So instead of here will be data size, it will be data size -1 semicolon is 0. So it's like from 0 to 31 instead of 0. It is 32 bits, as you all know. So we write 32 bits, we write in those format in Verilog. So going on, by this we are declaring like lamb. So this lamb will be of size 0, then will be of size 0 or of, let's take maybe the size of alarm, it will be maybe 1K for our, in our case, maybe not 1K, like we can take care to be 4K, which is 4, which is 4, which is 4 MB. So it will be 4096. So instead of 4096, it will be 4095, because we are just starting from zero counting. So we'll write in that format. So we'll close that one, and at the end we'll close with semicolon. Then from here, from there we'll now write now our how the lamb will be implemented. So how the lamb will work. So we use like the yeah we use the, or instead of large we will just implement. I think there is large and there is um ledges. So when we are doing here, we will use like always um at, so light at postage. So at postage I'll explain later. So at postage, I think basically, do you know how the clock it moves from 0 to 1, 0 to 1? So at the rising edge, when the clock is rising from 0 to 1, it's when now just uh it updates. Now if there was any kind of update, it will update you only the rising edge. So that's why I'm saying at the postage clock. So when clock is rising from 0 to 1, so it will be recording. So from there, uh in C++, we just, in C++ and other programming languages, we use curly brackets, but here we just like begin and end here. So basically that's like you have opened and closed at the end. So here we'll write now if reset is asserted. So basically it's like if reset is equal to 1. So I don't want to write more many kind of code. So just like if reset is asserted, which is if reset is equal to 1, then you enter inside, take lam, which I've declared up there. So inside lam we'll take now the, not that one, we'll take the right address. So right address, I think, yeah, right address, right address, right address inside lam. Okay, yeah, add right address. So I think here I will explain about this one. So this one is like non-broken. In Verilog it's called non-broken assignment, because everything, if we are working, because broken assignment will just allow broken assignment is when we are just putting like something like equal to. So this one will execute one thing at a time before going to another one. So I don't want that. I want everything to be executed at the same time. That's why I'm using unbroken assignment. It will not broke any kind of thing. So any kind of a variable or something. So I'll assign this one to B. It will be B and C. So I think if you are familiar with this kind of letters in hardware, that is like high impedance. And we have three kind of variables. We have 0, 1, x, and z. So most of the time 0 when it is not asserted, 1 is when it is asserted, z when it is high impedance, and x when the variable is unknown. So here we are putting now z because they will be, when you reset, it will be high, because we don't want to be seen what is on the address during the reset. That's why I'm putting that kind of high impedance on it. So address will record it to be z, which is high impedance. Else, right, else, so our else, because we do hold the different a lot of code inside, we don't want, we will just even start with a begin is like opening curly brackets. So because we will hold different kind of code inside it, so we just say if write enable. If you write enable is asserted. Okay, so enter inside lam. Basically will be write address will take the value of data in. Write address, I have said I will be using the non-blocking assignment, will take the value of data in. Okay, so we close that one, and if we write inside, because at the beginning we write else if, basically we just like if read enable. If read enable is asserted, uh, write, we will say that write address, or not write address, read address will take now. Okay, basically read address will take the data which was stored on the which was stored in the lam. So basically it will be lam read address, yeah, read address, is that so? Yeah, read address will take, okay, sorry, read address will take now, uh, will be assigned to data out. Basically no, sorry. Okay, data in, data out, I mean data out will take now the value on the address. So here it will be like lam read address. Yeah, why I'm saying this, like here if we write something on the address code 001, if we have just like on address 1001, data in, now address one will take the data in, will take the data which is right, which we want to write in the memory. It will take that kind of value. So here when read out, when the read enable is asserted, we'll just query that data from read address. So read address will just be equal, like it will be 001. Data out will have that kind of value from the data in. So that's how everything will run the module. So here that's all is about now. Our modules, our module will be lam module will work. So we have oh, okay, I forgot to end now. I think it could provide some errors, but let's close begin, that kind of begin after else you will write end. Yeah, so this begin will end here, this begin and here. So if you look in this side, so that's how, because first of all when reset is asserted, it's equal to this else, which means that when reset is equal to 0, it should begin. So it will also check when the write enable is asserted, you should write address should take the data, we should take the value of the data in, and when the read enable is asserted, then the data out should take the value which is on that, which was written in the read, which was written in the write address. So basically how now we are done with how implementing our lam. So lam will work in this format. Yeah, let me save, which is control O. So enter, we have saved, so we can close. So now we are done with our lam. So now we are heading to test bench on how we can write now test bench to test our lam if it is working correctly or not. Now we are going to implement the test bench to test our module. So basically I will be lighting the test bench, and the test bench also will be in Verilog, as we have said that earlier on. So we are going on here. Okay, so I will be using also nano. Okay, nano test bench. You just name it to be test bench .v. So basically the test bench will have to have the time scale and the other one. So time scale basically changes the default one. The default, it will run into picoseconds, but we just want to write in nanoseconds. So basically I will write something like this: time scale. Before writing anything, it will be time scale 1 ns slash 1 ps. So that's how we write first of all. I think basically I'm doing something like that. So we'll start with the module. So it's a little bit different when we are writing the module, our design in Verilog, which I was writing the LAM, and here in test bench. In test bench, we will just write module. Module, it will be test bench in our case. Then we'll close, not with some kind of the verb will be declaring inside. So at the end, we'll just end module. So that's all. We are done with the declaring the best one. So here we'll just declare now the input and the output which we put there. And first of all, this is a test bench. We'll just write like now local param. This local param will be like the period which to be running each and every time the clock when analyzing how many nanoseconds will be take to that for the clock to rise or to drop it again. So that's why we go on say local param. I use a local parameter. So I'll name it to be period in bracket then equal to 2. So this one we hope we'll see when we are doing later on. So let me put space. Okay. So here we'll write since input there it was like a y or something, so here will be like a range. So it will be range clock. So clock here will just not write that clock as clock, will be light clock and equate it to 0, so that it should start from 0 going to 1. And then you have range reset, and we'll have now like you go on, then we write that the interface, then we have two interfaces, light interface. If you remember when we were implementing our module interface, which is on port 1, which is on port 1. So here we have rage write enable, and the way it was we declared this, the name should be the same. We'll close also. It will be rage also. But here we write now the sizes of the size of the address and the stuff. So we declare to be, so here we also write, let's go on and write parameter address size, which we wrote add size is equal to, we say address size is equal to 11. We close, and the parameter will say parameter data size equal to 32. Write this in this format. Yeah. So here will be range address size. If you remember now, will be like add size minus 1 colon 0, which will be starting from 0 to 10 counting, then close, then it will be address, write address, and then we close. Then from there we'll go now to data in. So data in to be the same, to be reg, but here it will be data size. We'll be taking the parameter which is data size -1, then 0. So we declare, so this one will be data in as we declared in there in the module. So we are done with the write interface. We're going for read interface, on which is on port 2. Port 1, port 2. So here we have two input for this one, so we'll have two reg. It will be reg write, and not write, read enable, and then it will be reg read address, but here we'll say address size, because we write this side, this is the format -1, then 0, this is the format I will write. So here we'll just say read address with lot info. So we close. Then we'll have now the output. So what will our output will declare to be y, which is data out. It will be y, and because that side it was large, so we can put both sides. So it will have like the size, which will be data size -1. Then this, the way we do it, start from 0, counting from 0 to thing. Oh, sorry, it should be like something like that. Yes, so it will be data out, the way we wrote here. So now we are done declaring our variables. We are going in now to instantiate the duty. The duty is design under test. So design under test will call the lam the way it was our duty. So here we'll just call the name of the module in our lam. If you remember, it was lam. We ought to be lam. So it will be lam. But it will be lam duty. So the name of our lam will just name, the name of our duty will be just duty. So it will be lam duty. Here I think, let me put in caps here, to be lam duty. But if you remember, I think, yeah, we can put in that way. Will be lam duty. Then you just declare now, we'll map those kind of input variables with the variables we had declared here. So basically here we'll just enter inside. So here will be dot. So we'll be saying now the clock which is inside here with the clock which is from the other side, and with this one which we declared here. So we write just clock, open bracket, we write clock which is equal to this clock which is here. Yeah, to be something like that. So comma, then the other one will be reset. That's why we declare the value to be very equal, to be similar to those ones, so that we should avoid the confusion. So reset, it will be, yeah, let me close. So similar way with the write enable. So if you check the way I like the input variables here, it's the same with which I written in the lam. So here will be write enable, and close it, similar with the dot write address. It will be write address. Okay, similar with data in. So we write in this format where data in, it's also data in for the other one. So we are mapping now the variables here with the variables in the, so that this is a design under test. Okay, we'll close. Here it will be like read enable, from the data in, it will be read enable, read enable. So it will also be read enable the way we written there. We are going to read address, so it will be read address. So also here inside it will be read address because we written the same way. That's why I said it to avoid the confusion. Now it will be data out. The same way will be data out. Oh, sorry, be data out. The same way it will be data out also. So here we close, yeah, something like that. Then after closing, so we'll close with semicolon at the end. Then after closing, now we'll just declare the at always. This one always, this one will be putting the clock up and down, as you can see. So we'll be putting something like this, period which I declared on top there, it will be 2 nanoseconds. So it will be period divided by 2. It will be rising up and down the clock. Then period divided by 2. So 2 be divided by 2, it will be like 1 each and every clock second. It will be one cycle after 2 nanoseconds. So we'll just say clock is equal to, then tilde clock. Oh, sorry, I written a lot in caps, so it should be small caps because we declare to be small caps. So something like that. Then we close. After that, we will write initial. No, that's not the spelling. Initial. Then we begin now the simulation. Then end the simulation. So every simulation will write inside here. First of all, after 2 nanoseconds, we will put reset to equal to 1, which is like the reset is asserted. Okay, so we'll wait for another 2 nanoseconds. Reset to put it to 0 so that it should enter into something inside that kind of lamp. So we'll put it to be 0. Then we'll just add maybe on the fourth one, we'll put write enable to equal to write enable. Just let's say write enable equal to 1. Then after another, and the write address also, we'll just put like after those kind of 4 nanoseconds, write address will be equal to, so address we said it's 11 bits, so we'll just we'll write in this format, which is 11 nanoseconds. So we'll just put like something 10/10. So on this address, we'll just declare that write address is this kind of address. So after some nanoseconds, after maybe we'll add after like 4 nanoseconds, we'll put the write enable to be equal to 0, Then yeah, okay, I think not that one. After 12 nanoseconds, not milliseconds, nanoseconds, read enable is equal to what? We can say is equal to 1. We will raise now the read enable to equal to 1, so that we should be able to read. After the same, we can say like the read address should be equal exactly with this, because we are reading from the write data in, but we don't like we didn't write the data in. I need to write also the data in to put the data in. Okay, I'll put that one so that way, but the light address will be equal to similar address, so that you should take the data which has been written on that kind of address. So we write on address 1010. Let's go on top here. I think on the fourth we'll say data in. Let's say data in. After right, it will be data in. Maybe let's take in, put in a number, maybe 245, 44, something like that. Yeah. So after another 4 nanoseconds, I think you can write now those kind of yeah, something with the address will be written that one. So here after 12 seconds it will read from those kind of stuff. So now let's read enable is equal to be read enable is equal to 0, then close. Then after this one we want to monitor now on our the way we have inputted if it's true or not. Initial, then we'll begin again. This is for monitoring now. So from there we just write the $ monitor. So $ monitor, basically what they do is like it monitors each and every kind of operation which is being done in that kind of which is being done. So we'll open, then we'll close at the end. Then inside here we'll write time basically to be recording the time which is that kind of operation will be operating. So be like comma, then you open with brackets. So inside here we'll write now declare any kind of thing. So we'll start with write enable. Basically for the research it doesn't matter. So write enable is equal to, so I want to observe like the write enable in a decimal way. So that's why I will be writing $0 to remove the space in between. So after that, how can I demarcate it to be dot with those kind of dots? So I will just write, I will say read enable. So read enable equal to $0D. Then the same way. Then after that, I will say data in equal to $0D. Everything I just want to put in not in binary. It's able to read the numbers in decimal rather than in binary. That's why I'm putting the D1. So yeah, something like that. So I'll be saying data out, not real. I will be like data out to see now if we are getting the data. So data out to be $0D. So I have mentioned also the meaning of 0. So the meaning of 0 is remove the space in between. So we'll say comma in here. So just light enable, comma, I read enable, comma, and data in. This data in are those kind of declared in up there to be data out. Then that's the final. That's what we want to monitor at the end of the day. So basically I'll enter inside. So I just want to finish my simulation at 300 nanoseconds. I'll just write 300 nanoseconds finish. So that will finish on 300 nanoseconds. So I need to close that one also. So our simulation will end at 300 nanoseconds, but I need to put the end because I begin at the begin then end at the end. So that's what now our test bench looks like. Okay, so let's save and exit. So here, if you we ls, we have lam, which is our module, and the test bench. So what we are remaining now, we have to write two scripts, one to clear the space and the one to simulate. So I will start with the one to clear the space. So this one will just name it to be nano delete .sh. This is a script. So um I like working with the script rather than writing the command every time. So this one it will be um has been bash. So I don't like to use bash because in this simulation we don't know like the script. So basically most of the time I think for Linux it's better to use .sh because it's shell. So the script which I'm writing .sh, it can run in different kind of shells, whether it's a bash shell or other kind of shell. If you use bash at the end, um basically it's yeah specifying only the bash shell. So I don't want to be running on the bash shell only, so it can run in different kind of shells. That's what I'm using. Has been she. So yeah, so here on um this kind of script, so I will just like lm remove all. So when you are running that kind of simulation, you will experience those kind of files, which will be a lot of them logs and all the other kind of. So I will just um light those kind of. I will clear all of those minus file, remove all files which ends with the .log, and all files which ends with .jou. Remove all files which ends with .pb. Extension, remove all files which ends with wcfg. But this one is very important sometimes when you save, but I don't like to keep on this one. That's why I'm removing it to be very clear with the space. Remove all files which end with wdb. Yeah, so it will remove all those files. And secondly, remove the directory xsim. So I'll explain this xsim carry the logs for the simulation. Yeah, rf, which means like remove recursively all files which is in the folder called xsim. So basically it will just delete the folder. Yeah, we don't all names which have started, so it will be whether the different kind of um, all folders which have got xim, but we have got a different kind of extension, so it will delete it. So as we are done now, it's like let me save, control O. So that's one saved. So let me exit. If we look in that one, we have the folder .sh, but now I have to write the other one called simulate. I don't want each and every time to simulate, so I will just write simulate.sh. I don't want to write the commands each and time when I want to simulate. I will just be learning the script for it. So for the simulation, let me explain here. For the simulation, we have three, and in Verilog we have three stages. We have compilation, we compile the modules. We have the elaboration and the simulation. So elaboration, it will pick the top modules and for and those kind of files and this stuff. So basically I will write this script. So the script I will write for the whole. Even if I want to write if I want to learn other script using this script, it will also be learned just by providing the top level modules which have been used in the code. So I will just write the same has been share. So inside here I will not remove, so I will just learn the xvlog. Xvlog is for compilation. Over here it will be xvlog all files which end with .v. So all my files which is in Verilog to compile it. So the second one, it will be xlab, it's a elaboration command. So this one is timescale, which if you remember when I was lighting the test bench, I wrote on top of it. But when I was lighting the module, the lam module, I didn't include that timescale. So this one we will take and include on those kind of stuff. That's why I'm putting the timescale here. So I will write the same way, where 1ns slash 1 ps. So 1 nanosecond or 1 picosecond is equal to so here I'll run into two both one. So this simulator, it will be running into two, files. So I can simulate using uh, I can simulate in CMD or simulate in graphical. So in graphical, we will be using Vivado. So first of all, let me start with the learning in the module. So here XLab will just include the top level module in the test bench. So here we will just write test bench in our case. Yeah, so this one is just we are running for specific, this script is for this specific kind of this script is for the specific file of this project. So uh, it will work. That's why I'm specifying. But if I was using for different kind of, I would light the top level so that it should be running. But this one will just specify for this kind of project of RAM. So I want to simulate it using this one. Will be a script running for the CMT. So at the end now we'll simulate. We'll say xsim. So under xsim, we'll just select xsim test bench. The test bench is the top level module in the test bench. I wrote it to piece. Then at the end, you will just say minus r. So this one will compile in CMD. So I will save, Control O, then exit. So if I OS, it can't run. We have delete.sh and simulate.sh. But when you are running, we have to give the permission, executable permission. Because if you look like AOS minus LA for all modules, if you can see the simulator and test bench, they cannot be executed. We don't have executable. Executable is x for the groups and the so I'll give them the execution. So I will just write chmod plus x, it will be test bench, not test bench, it will be delete.sh, and let me give for simulate. So if I check now, they changed even the color. So they have let me, yeah, we have the x for the simulate, and they have x at the end for the what, for the delete. So now we are okay, but we will simulate in the so let's check if there is an error. So I will run now the simulate one. Go on and run the simulate. We have an error near syntax error in lam.v near line number 19. Yeah, so I'll go on in lam.v line number 19. Near age. Okay, it's around, yeah. I like to I like out instead of output. If you check here, it will be output, not out. That's why I was experiencing those kind of error. So I'll just save. Yeah, so if you ls, there are some of the file which came.pp.log. So that's why now I can run delete to remove those kind of files. So if ls, now we have remaining with only, so that we will clean up. That's why I created those kind of this script to create this workspace. So I'll go on and run the simulate one. If we have an error, we'll rectify. We have another error somewhere. I think the syntax error near in test bench line number 47. So we'll go into test bench. That's where we have an error. Nano test bench line number 47. Okay, line number 47. Okay, of course here it will be like difficult to know which number 47. Okay, let me run in get it so that you should be able to set the numbers. Exit, get it, test bench. So okay, display line number now line, so line number 47. Just saying there is an error. Where is an error? Where is the error? Where is the error? Line number 47 is this one. There is an error near, so I don't know. Address 11, id address. Okay. Okay, so I think id address is equal to, okay. So let me check on again. Syntax error on line number 47 near this one equal to, I don't know where the problem. Okay, near line number 47, it might be there, line number 47, or somewhere else. Line number 47 near, it might be at the bottom or read. Oh yeah, I have an error here. I have to put the number of nanoseconds. So nanoseconds I will put maybe like 14, then something like this. So I forgot about this one. So this is kind of errors which we experience each and every day. So now I have rectified. Let me clear my workspace because I have some of the works I think inside. So we'll go on and simulate. Yeah, I think now we don't have an error. So let's check if we have compiled already. Yeah, now it's in the simulating part. Yeah, so as you can see here, we have like the on 0 we had the light enable x, so light enables 1, so lead enables x. We don't know, that's why coming x is unknown. So data in also it was unknown, and data out it was unknown, which is x. So light enable is 1 on 12 seconds on this one. So data in was the 244. Data out was unknown because read enable was unknown also. So coming here, right enable 0, read enable is 1, data in still was 244. This one was unknown. So here it's 1, but here because it takes some, if you can look, this one we say there is a blocking assignment and unblocking assignment. So I can test better used like the blocking assignment. That's why it takes some time to save some kind of sign some of the things. So here now we are getting data out at 244. But if you remember, in our test bench we didn't provide the data out. We are getting from the same address which we wrote in the light address. So this one with the simulating in CMT. So to simulate in Vivado, let me edit. Okay, let me just do this. I need to copy this and change somewhere. We just get it, simulate. So this one, let me copy this one, copy. Okay, and I will just get it. Simulate. In this time it will not be simulate, it will be simulate GUI, which is graphical user interface. Just creating. So I will just paste it on what we have on. But what I will change here for the graphical one, I will just say debug or debug or here instead of -r it will be -g, the small g. So we just save this. That's the only difference between simulating in CMD and the simulating graphically. So if we LS here, we have the simulation, but we have to provide now the permission to execute those kind of yeah. So here what I will just do is just simulate a GUI dot .sn. So just yeah. So if I OS here, we have the log. So let me clear the workspace. So now we have this working file. So we have a simulate GUI and simulate. And this one simulate is like the one where which I learned that one. That now I will just learn now simulate GUI. Why yeah, something like this. So now it will learn in Vivado instead of using the CMD. So that we need to see what is going, what is happening if our LAM is working properly. Yeah, we just need to be patient a little bit. It will come. Yeah, the Vivado is coming now. I'm using Vivado 2019 version, and it's from Xyrene. You know, as Vivado is being developed by Xyrene. So let me expand this one to be able to see properly. So here we have in our test bench here we have this one. We need to add to the waves. Right address, yes. Okay, and the data, yeah, something like this. So this one I'll add to window web, but let me divide this one. Here I'll add the divider so that we should be able to see. So this divider, um, the main divider. So just light something like that. So just push on top, and from there, I'll add another divider. So this divider will be right interface. The way I wrote somewhere there, light interface in the code interface. So what light interface will do, we'll start from there to see, and we'll create another one. I think we'll create another one here. New divider. This will be read interface. But to be familiar with, we have to change the color of the divider. The light, let me give green, and this one let me give color, let me give to be yellow. Yeah, something like that. It's gold, of course, but we are color blindness. So here, after that, learning that, we can learn now our simulation to check if it is working properly. Um, this is a way. Now let me expand this one. Yeah, this is it. Yeah, so we'll expand it again. So if you are checking now here, as you can see, reset here it was 1, so nothing here. That was x unknown unknown unknown. But reset after being 0 here, reset is 0 being 0. Now here light enable is 1. So light enable was 1. We are able on light address we had this. So let me change to, yeah, it should be unsigned decimal. It was 10, and our value here, let's change to be in binary so that we should be able to see properly. Unsigned decimal, yeah. So here unsigned decimal, it will be also in decimal. Here it will be unsigned decimal. Okay, so here we are able to, on address 10, we provided address 10, and data in, we are able to write on address 10 on 244. So on lead enable, uh, here on lead enable, when lead enable is 1 and we provided the lead address, on the same one address lead address to be 10. So I wrote 1010, but it was in the 11 bits format. So it was 10, the number is called 10. So on address number 10, I called the address number 10. So it was able to give us now the same value which we wrote on address 10. So our alarm now, we can say that it's fully working. We are able to see how alarm is working now. So that's it. So basically what you have done the configuration here, you can save, but basically you don't want to save. That's why our alarm is working. You are able to write on address number 10 144. You are able to get the same 144 on address number 10. Thank you very much for being patient with my video and for being attentive. Thank you.